So we're looking at Theorem 14, Theorem of Pythagoras, where you're given a triangle ABC, like this one here, where one of the angles is 90 degrees, BAC in our case. What we want to prove, well, if we know Pythagoras, and hopefully we do, we want to show that this side squared plus this side squared equals the hypotenuse squared. So for us, that's AB squared plus AC squared equals BC squared. Now our construction in this example is a line through A that is perpendicular to the base, and you call the point where that lands D. Okay, so there's our construction, and because it's perpendicular, we've got two right angles here. Okay, now I have another triangle here. I'm just going to sit in on top of that. That's the same one. Okay, and you can see I've marked a few angles in it there. So our construction is the line AD perpendicular to BC. So our proof. Well, this rests on the idea that what we've just done is broken our big triangle up into two smaller triangles, both of which are similar to the bigger one. So we'll start off with this small one here, which is the triangle ABD, and I'm just going to spin it around so that it lines up. Oh, excuse me, I have to flip it over so that it lines up with the one above. Okay, so this angle here, that's a common angle. In fact, let's mark in the points first. Okay, that point A, if you see, landed down here. Okay, D is at the angle D, at the right angle, and B is the last remaining point. Okay, so when it lands over here, I can say, oh yeah, that's a similar triangle because this angle is in both of them, and they both have a 90-degree angle. So this triangle here is similar, that big one is similar to this small one, which means corresponding sides are in proportion. So we can write down a fraction of certain sides is equal to some other ones. Now the fraction we are going to go with is BD on the small triangle divided by its corresponding side AB on the big triangle is going to equal BA on the small triangle divided by its corresponding side BC on the big triangle. Okay, BA, I should have called that AB. It doesn't matter what order you do, but you can see that you've got AB in two places here, so that's why I've done that. Okay, well, in saying that, if we cross multiply now, we're going to get that BD multiplied by BC equals AB squared. And that is part of what we're working towards in our proof. Okay, now coming to this triangle, the other small triangle. Okay, you can see again you've got a common angle in our big triangle ABC and this small one, and again you've got a 90-degree angle in both. Okay, so again you're going to find that they're similar triangles. You just flip it around again and they line up here. Okay, now what goes where? Well, again, that right angle there is where D was. So this point here corresponds to D. Okay, this point here is C. Now we have to flip it over, but that's still C when we land in there. And this point over here is A. Is A again. Okay, so actually that's A for this triangle, and this is A for this triangle. And that angle there is in both triangles. You can see it there. Okay, it's in both of them. Now, so we have an angle and a side in common. So we've got similar triangles again. So that means we can say that DC in this triangle here corresponds with AC in this triangle. So DC divided by its corresponding side in the big triangle AC will be in the same ratio as AC in the smaller triangle divided by its corresponding side BC. If you're wondering which sides to pick, the general rule as you work through this theorem is stay away from AD. You'll never be interested in that middle line. It's always the three sides of the big triangle is what you're working for. So even though you could say this equals AD here, AD divided by, in the corresponding triangle, it'll be AB. You're not interested in that side, AD, ever. Again, cross multiplying. DC multiplied by BC equals AC squared. Okay, and that's another thing that we were looking for. So to start with, the proof will say, if I call this angle 1 and that angle 1, okay, sometimes like that, and if I call this angle 2 and this angle 2, I can say triangle ABC, our big one, and triangle BDA are similar, as the angle 1 is a common angle. It's in both triangles, and both have a 90-degree angle. Okay, so that means they're both similar. Therefore, I can come along and say this thing here, okay, that BD over AB is equal to AB over BC, and that gives us that AB squared equals BC multiplied by BD. Okay, so that's where we were there. A very similar argument gets us to here, that triangles ABC, again, the big triangle, and this triangle ADC are similar because 2 is a common angle and both contain a 90-degree angle. Okay, so that lets me say this thing, that DC over AC equals AC over BC, which gives me AC squared equals DC multiplied by BC. Sorry for squeezing that in there. So we've got AC squared and AB squared. We've worked that out, so let's put them together. We said AC squared plus BC squared equals, now sorry about this, I'm going to have to go back. AB squared was BC multiplied by BD plus, that was BC squared, sorry, that was that should be AB squared plus AC squared, very sorry about that. So AB squared gives BC times BD, and AC squared gives DC times BC. Okay, so we're nearly finished. We spot here BC is a common factor. So you can say BC multiplied by BD plus DC, those two lengths added together. Now if you come back to our original diagram, BD plus DC, BD plus DC, well that just all together makes up BC. So that's BC multiplied by BC, or BC squared, and that's what we were trying to show as required. Okay, or QED, so it is demonstrated, quod est demonstratum. Okay, there's Pythagoras' theorem.